The recording will be available in a couple of days on our website. It should take about 20 minutes today, and at the end there will be time for questions. If you could please type your question into the provided space, so in the question space. As for technical purposes, everyone is muted by default. Okay, so I think that's all of the housekeeping announcements, and we can start. The agenda for today. We start with the impact of gridding with faults on volumetrics, and then we will discuss how to grid fault planes using Z values on faults. Then I will do a short demo, and we will summarize everything. So why should I grid fault planes? What I do with the fault planes has a huge impact on volumetrics. So if I leave the fault planes blank, I have areas with missing data, like over here within this fault polygon. And this means missing volume, as the software cannot calculate the volume under the fault plane. So this chunk of volume will be missing. If you're calculating volume in heavily faulted structures, where faults constitute a higher percentage of the area, the volume will be largely underestimated. So it is very important that you grid the fault planes in order to capture the volumes. How to grid fault planes in Petrusys? There are three ways of doing it. The first is a basic method, and this method is very simple. So in the gridding panel, in the faults tab, turn keep inside faults on. So in the bottom left part of the panel, check this box here, keep inside faults. And this method uses only one gridding algorithm for the entire grid, and it works well with some data sets. However, because only one algorithm is used, it has its limitations. And when we are gridding more complicated data sets, the areas of the grid within the faults may not always be a perfect representation of a plane. So if this happens to you, you can use the three-step method of gridding, so the second method here, and this method grids the faults in 3 steps. So in the first step, it grids as normal, but we turn off keep inside faults that we use in the basic method. And this blanks the faults, so we have no grid values within the fault areas, just over here. In the next step, we use the output grid from the first step as input for gridding, and this time we deactivate the fault data tab. And we also use linear algorithm. So what happens in this situation? We have only one input for the gridding, so there is no faults. There's only the grid from the previous step. So it looks like this. So we have a surface on one side of the fault, on the upfront side of the fault, and then on the other side of the fault we have the continuation of the surface. And then there is a gap between where normally there would be a fault. And what happens here, the gridding process will fill this gap with grid nodes. So between the upfront side of the fault and the downfront side of the fault, we will have a nice plane. And this plane will be formed really nicely because we used the linear algorithm. So it models better the plane surface here. In the next step, we will merge those two grids. So we will fill the gaps in the first grid with the fault planes from the second grid. And as a result, the contours will now be more parallel to the fault plane, and it looks more realistic. So it can give you a more realistic, geologically realistic results. And as this method uses different algorithms to model different parts of the final surface, it can help create just better grids, more realistic grids. So just to compare those two methods, the basic method uses one algorithm for the entire area of interest. Usually this is minimum curvature, which is the default algorithm used for gridding in Petrusys. And it works with some data sets. However, sometimes you may find that it produces completely unrealistic results, like the one that I used over here to show you. In this situation, we can use the three-step method. And this method, first, we grid and blank inside the faults. Then we grid fault planes using linear algorithm, and then we merge those two. Okay. So the next method now is gridding with fault Z values. What are fault Z values, first of all? They are two-way time at depth values at the areas where the fault and horizon intersect. So in the cross-section it looks something like this. We have a horizon, and we have a fault, and we have interpretation points along the horizon. And as the last interpretation point falls somewhere here, if we have no z values on the fault, the algorithm will extrapolate from the last point towards the fault. If we have z values on the fault, it will tie nicely this horizon with the fault. So we have a more accurate surface in the proximity of the fault. So the fault z values method, to use it in the gridding panel in the fault tab, take use z values on. So it's just over here. What to do if you don't have z values? You can grid using the basic method, so just keep inside the faults. And then there's an option in the surface modeling under gridding dump fault file, which allows you to back interpolate z values from the grid onto the faults. So we now have z values on the faults to use for gridding as well. And why would I bother gridding with z values? So gridding without z values can create geologically realistic surfaces, as we've seen in the previous method, but it doesn't know where to tie the horizon and the fault plane together. So I highlighted here the contour 2140 in red, and you can see that at the fault intersection with the horizon, there's sometimes quite a large mismatch between this contour on the horizon and on the fault. Gridding with z values on the faults helps to eliminate this mismatch, and there is a very good tie between the horizon and the fault. So as you can see over here, this contour now matches at the fault intersection with the horizon. The other important parameter that has impact on gridding with faults is a grid cell size. So in this example, I'm using a grid cell size of 200 by 200 meters. And as you can see, the faults, the fault polygons are much narrower, so the width is about 85 meters. This is due to their steep dips. So the dips are about 65 degrees. And for the software to be able to notice the faults, there must be grid nodes inside the fault polygons. So as you can see over here, where there is a grid node, the fault polygon is also filled, color filled. Where there is no grid node, there is missing value, and the area is blank. So to capture the fault, we need to resample this grid to a smaller cell size. So I'm using now 10 by 10 meters. And in here, always remember, you don't need to, and rather do not regrid this grid at a smaller cell size, as this may introduce bullseyes into your grid. So rather use grid processes resample option, which will honor your input data, the original input data. Okay, and now we can move to a demo. So I have here a GoFax dataset and the top at horizon. And I'm using 2D seismic lines. I'm going to grid those 2D lines using also faults, so I can just turn them on just now. And I will use those three methods that we discussed for gridding. So in the surface modeling, I have prepared a workflow which starts with the basic method, and then it moves on to the three-step method, and then it grids with fault z values. And at the end, we will also look at the volumetrics. So we start with the basic method, keep inside faults. So I'm using the 2D data from my SDF seismic data file, and I'm using also faults, and I just take the keep inside faults over here on. And I ran this grid before, so I'll just show you the results on my map already. Just switching the faults on, and this is the result of this basic gridding in this particularly faulted area. So as you can see, the faults, they really don't look very good. If I zoom in closer on one of them, you can see the fault plane is really not very well modeled here, so I'm not happy with the result. Other thing is that I probably used too large cell size, and not some parts of the faults are not captured here. So I'm not happy with those results, and I'm going to use the three-step method to refine it. So in the first step, I will blank inside faults. For this, I will use again the same input data. And I will also use fault data, but this time I will switch the Keep Inside Faults tab off. And the result looks something like this. So we have a surface with blanked faults in here, so there are no Z values within the fault polygons. Now I will use this grid as an input in my second task. So I'm using the blanked grid as an input, and I'm also switching the fault tab altogether, so I'm not using faults at all. And in the methods tab, instead of using the minimum curvature, which is my default and usual method of gridding, so gridding algorithm, I'm using the least squares plane algorithm here. And the fault planes are now really nicely modeled, so we can see that there's a nice plane, the contours are parallel to the fault plane, so it looks much better than my previous result. So now I can merge those two grids. For merging, I'm going to use the formula from our templates. Gridding operations templates, grid operations template, replace missing. And this will replace the missing values in the blanked areas of the first fault with the values from the fault planes when I use the linear algorithm, so from the fault which I graded with the linear algorithm. I'm also using faults here to embed them into my final grid, and this is my final grid. And this looks much better than my first attempt, so I'm more happy with it now. However, when I highlight the contour again, 2140, in red, you will see that again I end up with a mismatch here between the contour on the fault side and on the horizon side where the fault and horizon intersect. So to eliminate this, I will try to grid with the fault Z values. So first of all, I need to back interpolate the Z values from the grid. So I can find this option in the grid menu, dump fault file. And here I'm using the grid that I created in the first method, so the basic method, keep inside faults, and I'm back interpolating Z values to my fault file. And once I have Z values on the fault, I will use it for gridding, and this time I will grid again just 2D lines, use fault data, keep inside faults, but this time I will also use the Z values on the faults which I just back interpolated. And the resulting grid as shown over here. So you see that this process helped me to tie up the contours nicely at the fault and horizon intersections here. So for my dataset, I think this was the best method. And now I would like to have a look at the volumetrics, the impact of volumetrics of those 3 different methods. So I have here 4 volumetrics tasks. The first one uses the blanked areas, so the faults with, so the grid with faults with blank areas, so the blanked faults, and also as a top here, as top grid here, and also reference level at the 2000. For the next volumetrics task, I will use exactly the same parameters, but I will just swap the top grid to keep inside faults, so the output of the basic method. And then in the next one I will use the output of the 3-step method, and in the next one fault with Z values method. And I've ran those tasks before, and I've collated the results for you in my presentation. So if I use no faults, so if I don't grid faults at all, the total measured volume reported here is 2.19 cubic kilometers. If I use the basic method, the total measured volume is 3.32 cubic kilometers. So you see that there is a difference of over 1 cubic kilometer when I'm using faults or when I'm not using the faults. So it's very important to actually grid the fault planes. If I use the 3-step method, now the total measured volume is refined better, and I've got 2.38 cubic kilometers. And when I'm using the fault Z values method, the measured volume is 2.72 cubic kilometers. So each of this method actually reports different volume. So it's very important to create geologically realistic and the most accurate surfaces to use for volumetrics later on. And just the final thoughts for today. Always grid fault planes, so to capture the volume. If you have Z values that you can trust on the faults, you can use them for gridding as well. If you don't have Z values, there are ways of back interpolating them from the grid. So just as I showed you before, you can use this method as well. Choose the best method of gridding for your data set. If you see that the result is not really satisfying, always try another method. Do not be afraid as well to use the 3-step method, which maybe sounds a little bit complicated when you hear it the first time, when you see it the first time. But you can save this workflow, which consists of only 3 tasks, and reuse it on your data. And I also saved this workflow. I can send it to you, and I think I will send it to you in the follow-up email today. So you can just use it against your raw data and it will be easier. And always think about cell size as well when you're gridding faults, just to capture each fault and all area of the fault, as much area as possible, as the cell size will determine how much faults you can capture as well. So thank you very much for your attention, and